Hi, welcome to a lecture on C++ literals and constants. Right. We've previously talked about data types, which we need to have some knowledge of data types for this lecture, as well as later in the lecture, we're going to declare some constants of certain data types. So we need to know the variable naming rules as well, which were covered in previous lectures. So a literal is just something that is a fixed value constant that our program can't alter. Whenever we write code, sometimes we actually hard code values into our programming statements, right? We might hard code in, so there's some examples here of some of the basic types. An integer type, the number 42. Floating point numerals, 2.5. So this is an integer type simply because it's a whole number, no decimal point, right? A floating point value, that family has a decimal point in it. So 2.5 would be of a floating point type. We're going to see that later in the lecture slides. 42 is of type int, 2.5 is of type double. Character literals have single quotes around them. So that's how we know, that's how the compiler knows, and how we as humans reading programs know that this Z with the single quotes is a character and not Z, the name of a variable, right? And the name of variables can't have single or double quotes in them as well. So that is what differentiates the two. A string, any characters within a left double quote and a right double quote, so within double quotes, is a string of characters. So its data type is referred to as a string in C++. Boolean types, well, those literals can just be true or false, all lowercase, and those are keywords of the language. So integer literals, when we're writing them in our code, we can write them in base 10 form. So decimal is base 10 form, octal is base 8, or hexadecimal is base 16. So we can write constants in any of these three bases. But by default, when we write a number, if you look down here under examples, 43, the compiler interprets that as base 10, which makes sense. We do all of our math in base 10. We do our thinking generally in base 10 because that's our most commonly used base, right? But if we want to write a number in hexadecimal, then we'll specify a prefix before the number, and that prefix can be a 0 lowercase x, or it can be a 0 followed by an uppercase x. So it's always a 0 followed by an x. It doesn't matter whether the x is upper or lowercase. So down here in this example, 0x43 says that the symbols 43 are written hexadecimal. And then if we want to write something in octal, we put a prefix of 0 in front of that number. So if you want to write something in base 8, so if you write 043, the compiler will interpret this as a base 8 value. So each one of these, right, is a different value. This is decimal, 0x is hexadecimal, and 043 is octal. So those are prefixes that we can use then to tell the compiler what base we're writing in. Right. And when it comes to the hexadecimal integer literals for A through F, right, you can use upper or lower case. So again, 0 small case x, so we can use the small case x or the capital case, uppercase x, right? So if we want to write the number 4a, right, you can see that we can write 4 with a lowercase a in hexadecimal, or 4 with an uppercase a, or we can write this form, 0 capital X for lowercase a, or 0 capital X for uppercase a. So these 4 different ways all specify the same hexadecimal number. So pick a style and stick with it. All right, just remember that the 0x says whatever follows is written in base 16 hexadecimal, and any of the hexadecimal symbols, A through F, can be upper or lower case. You can also assign a suffix to an integer literal. So the prefixes denoted the base. The suffixes can be used to specify the type. So if we just write here under examples, the number 30, that literal is of type int, right? If you want to make this literal an unsigned int, you write 30u, and the u can be an upper or a lower case. Right? So the suffixes we can add over here, uppercase u or lowercase u, uppercase L or lowercase l. I tend to use uppercase L because lowercase l sometimes looks like a 1. So I find it personally, I always use the uppercase L. It's easier for me to read and not confuse the lowercase l with a 1. Right. The suffixes can be combined in any order. So here our 30 uppercase L, that says that this data type is a long, right? Remember, if you just write 30 all by itself, the data type is integer. If you write 30L, the data type is long. If you want to make it an unsigned long, you can say 30UL or 30LU. So this is when we say the combination of suffixes can be in any order, right? The U can come before the L can come before the U. You can mix the cases as well. And you can also specify for hexadecimal a different data type. So if we go back here, right, we said if we write 0x in front of our integer digits here, that makes the base hexadecimal. Right? That makes the base, so 0x43 makes the base hexadecimal, but the data type of 0x43 is an integer type. If you wanted to make this a long, which is what we're doing here, so 0x, FE, those are hexadecimal symbols, right? This is basically 15 by itself and then 14 in base 10, but specify the suffix L there, and it says that this particular literal constant value is a long. Now, typically what we're going to work with, we're just getting started programming. We're just going to try to work with ints because we don't want to try to remember all of this immediately, right? It's chapter 2, you're being given a lot of information, and until you use it like anything else and practice it, you don't get used to that, and you don't want to try to memorize all this. So the important thing to remember about these integer literals, I'd say for now, the important thing in our first couple of assignments, because we won't typically ever use octal in this course. We will use hexadecimal later on. But for now, when we write values, we're going to write integer values that are base 10, and they're going to be of type int. So there's no suffix that we have to give it to make it type int. Later, when we work with special numbers that need to be unsigned long, and we'll see that it's important to actually then make sure we match data types as much as possible when we write our code, then we'll come back and review some of these suffixes at a point when we need them. Floating point literals, right? So when we write floating point in our code, it's going to be of type double. To remind you then what a floating point number can have, right? A floating point literal can have an integer part, a decimal point. So here at 3.14159, the integer part is the portion to the left of the decimal point, the 3. Here's your decimal point. The fractional part, well, that's the point, that's the 14159 to the right. And if you want, you can write things with an exponent as well. And you can leave the exponent off. If you leave it off, we just assume that it's multiplied by, well, a 10 to the 0 power is a 1. So we don't even really think in terms of exponent parts. What I remember is if I have a number that I need to write in scientific notation, is that I can write that number if I use the E for it. We don't often write constants like this in our homework assignments, but sometimes whenever you're working with, say, maybe some scientific constants from chemistry or physics, you might want to write them in their exponential form. They're easier to write and to print out that way. So you can see here, instead of saying 3.14159, we could also say 3.14159 e to the minus 5. So that's 3.14159 times 10 to the minus 5. So this always assumes that you're going to multiply by 10 raised to the power that you have on the other side of the e. Here, 1.0 e to the 6 is 1 times 10 to the 6th, or 1 million. So it's faster to actually write something out like this than to try to write 1 followed by 6 zeros. It's easier to read this. This is a little more common in terms of numbers we might write. So this example here, you don't necessarily have to write the integer to the left of the decimal point. So if you, instead of writing 0.3, we could write 0.3. And in this case, this is 0.3 times 10 to the minus 2, right? So it's just another way of writing these floating point numbers. Remember, floating point numbers have a decimal point in them. Oh, and the signed exponent, the one thing I didn't mention is it can be a lowercase e or an uppercase e. In the examples I gave you, right, I'm using the uppercase e, but you could easily replace that with a lowercase e. Again, when we need to use these, but we'll use some in practice later. Now, by default, whenever you write a floating point number, here's what you should remember, that it's of type double. So a floating point literal data type is double by default. Just like the integer literal by default was an int type, right? The floating point is a double. If you want to make it a float, then you can add the suffix lowercase f or uppercase f. So here's some examples. If in your code you write 1.23, its data type is a double. Showing that in comments to remind you, right? 2 forward slashes, anything to the right of that is a comment. So I sort of wrote this in C++ form. If you write 1.23 with a lowercase f, the data type is a float. If you write 1.23 with an uppercase f, data type is a float. So if we don't have a suffix with a floating point number, we know then that it's a type double. If we want to make it a float, we use the f suffix with it. And I've got positive numbers here, right? You could easily make this a negative number as well, because remember, floating point types represent negative values, positive values, and 0. All right. Character literals, right? As we mentioned when we started this set of slides, character literals have a single quote around them. So you always enclose them in a single quote. It can be any sort of character that we have, like we've taken a look at an ASCII table, but depending on what your character set is, it can be any character from that character set, and that's normally a single character, but it can also be an escape sequence. So we've seen the escape sequence \n for a new line character. That's basically then the one time when you would have more than one character in here. So here, this example of a lowercase a with single quotes around it, we ask you the data type. The data type is char. Oh, I don't know what's happened to my tabs here. It's a bit ugly to read. Let's tab that back over and correct that. All right. So a 1 with single quotes around it, its type is char. If we had a 1 with no quotes around it, it's an int type. Right. X with single quotes, type char. Escape sequence \n, it's type char, right? And that's just a reminder that it's the new line character. There are other types of character data as well. We won't be working with a wide character data type in here, but if you're ever looking at someone else's code or looking at examples on the internet, wide character type data is preceded with an L. And notice it's still wrapped in single quotes, but it's preceded by an L. That's not something that you have to know for this class, but if you want to use another character set, I've got a reference to Microsoft has a good listing of all the various of different ways. There's many different ways to encode characters. We'll typically just work with the ASCII encoding in this course. So important point is single character enclosed in single quotes is of type char. If there's more than one character enclosed in single quotes, it has to be an escape sequence to be valid, and it's of type char. And here's some common escape sequences then, right? Your \n, your new line, your \t is your tab. And then when we want to print out things like a \, since a \, indicates to the compiler that this is the start of an escape sequence whenever it's found either as a character or inside a string. If we want to actually print out a backslash, we have to use backslash backslash, so it prints out 1. If we want to print out a single quote, we say backslash single quote or a double quote backslash double quote. So out here on the right is an example C++ program. And I encourage you to go ahead and type this in and run this. So if we look at this first line, remember C out causes things to be printed on the screen. And we're printing things inside the string here. So the double quotes. Now this, remember we said anything within double quotes is a string literal. So this is a string data type. Everything within these double quotes is a string literal, and it's a string data type. Right. That will print out 1, 2, 3, 4. The new line character says to go to the start of a new line. So you can see in the output. So remember our statements execute from the first line of main. This is the first line of main. So this is the first statement that would execute in your C++ program. So it's going to print out the 1, 2, 3, 4. The new line character says move the cursor to the start of the next line, and then go ahead and print the rest of it 5, 6, 7, 8 out on the line. Right. And I actually left an extra space there. We can't necessarily see a blank space after the 8, but it actually would have printed that blank space as well. So after this, so after it prints out the 5, 6, 7, 8 space, then endl is another way of saying move the cursor to the start of a next line, right? The backslash n is an escape sequence way. This is endl is a C++ way that's been defined in this IOStream library, and it's think of it as very similar to the backslash n. It just says move the cursor to the start of a new line. So that's why after the 5, 6, 7, 8 here, when this next statement cout executes, it starts with printing the 1, 2, 3, 4 on a new line. So 1, 2, 3, 4, excuse me, backslash t is the tab. So you can see it tabs over and then prints the 5, 6, 7, 8 in the space on the same line. This endl says go ahead and move your cursor and your output to the start of a new line. So now we're going to print out the characters of the word backslash, colon, space. So backslash, colon, space. And in order to print out then a single backslash, we have to have 2 backslashes together here. And you can see it prints out the single backslash. So that's that escape sequence. And you can see similarly, right, in order to print out the single quote, here we use the backslash single quote, and single quotes here, backslash double quotes there. All right. So most commonly, you'll probably use the backslash n. The tab, the way the tab usually works by default is it tabs over and it starts in a column, in an output column. So if you think of the columns as 0, 1, 2, 3, 4, 5, 6, 7, 8, columns that are evenly divisible by 8 is usually the default in a terminal. That's a bit of trivia. All right, we'll find better ways to output, to format our output if we need to do neat formatting than just the tab character. String literals, right? We just said that a string literal is enclosed in double quotes. So it can be a sequence of 1 or more characters enclosed in the double quotes. So here's an example of an A, a single character A inside double quotes, but the data type of this is string simply because of the double quotes. So remember, double quotes is string, single quotes, so this A here inside the single quotes is type char. Right? Double quotes means type string, single quotes means type char. Here's an example, right, of a longer word, hello in double quotes. You can have any character in there, right? Here's 1, 2, 3, ABC. Both of these data types are string, right? These are string literals. And sometimes we find it to be useful to have to break things across multiple lines using string literals and separating them. So here's ways you can do this. Right, so here's one string literal, hello, comma, space, dear, right? All in one string. But if you wanted to then end up with the same effect using multiple lines, you start with the double quotes. You say hello, comma, space, And you can decide, you can put the backslash anywhere. In this case, you put a backslash, and that backslash says to the compiler, this string will be continued on another line. And you can even skip a blank line, as was done here, and then go ahead and finish up your string later. So if you have some long string message to print out, right, we try to never go past the 80th character in our text editor, right? And so you want to break strings up. So that's one way to do it. Another way to do it is you could have multiple string literals that you print out. So you could break this into double quote, hello, comma, space, double quote. There's one string literal. Here's another string literal D. Here's another string literal EAR within here, right? Depending on how you see out, you could get this to all print out as hello, dear. I said, most of the time, something short like this, we're going to have inside double quotes. When we write some code with some longer strings, we'll go ahead and see an example of using this backslash to actually then tell the compiler that the string carries on another line. Boolean literals, where those are C++ keywords, it can only have two values, true or false. They have to be spelled as shown, all lowercase. All right. So naming constants, right? We often then sometimes, so what we just saw were constant values. They were literals that we might write in our program, but we actually might want to use variable names or identifier names to name a constant. So a new keyword for us, const, const for constant. This is a prefix that's used to declare a constant with a specific type. So we're going to say const type name, so that's your data type name, then our variable name, and then we need to assign it a value. Okay, so here's some examples. This modifier then, this prefix const says, const double says create a variable of data type double. Its name is pi, set it equal to 3.1415. What the const says is that once we go ahead and declare and initialize this, you can never change in code what's stored in pi, which makes sense. If you want to make a constant for pi, pi always stays pi, right? We don't do anything to change it. So we'd want to have a way to use this variable name in our code and prevent accidentally overwriting it. So the const prefix says this has to be held constant throughout the program. Now, by convention, constants are named using all uppercase. So they follow the identifier naming rules, but we write them as all uppercase. So as we're reading someone's code, if you follow this convention, when you see something written in all uppercase, you assume that it's been declared somewhere as a constant and shouldn't change. So here's a couple others, const int length. So this variable with name length is of data type int. It's assigned a value of 12, and that will be a constant value and can't be changed. Any data type we have, any of the built-in data types we're working with, char, you can create a const char, you can create a constant string. So any of these, you can create a constant Boolean if need be, but you can create consts with any of these built-in types we've been learning. And here's the important thing. When you declare this variable, this constant, and so remember the word variable in programming is the name of an area in memory. So don't think of variable as something that varies, because what's stored in it can't vary when we say it's constant. Right. Terminology is probably not the best, but it's the terminology that's used in programming. So when we go ahead and declare this variable, we have to initialize it. Right. So if we do this, const double pi, remember we said whenever we declare a variable, if we don't store something in its memory in the built-in data type double, that it has a garbage value in there. It has whatever value happens to be sitting in memory in your computer, right? If we then afterwards try to assign a value to this, it will cause an error, right? I've got an example here, right? So remember, the const modifier says it can't change. So here's a C++ program where inside main, I declared this variable pi of type double. I said it was constant, right? Initialized it with a value. And then later in code, so down below, I accidentally write something like pi equals 5. Well, the compiler, because we use this prefix of constant, then whenever we try to run and build our program, generates this error message in function int main, right? And the name of this program was constants.cpp. That was the name I gave it, right? It says error, assignment of read-only variable pi. And it shows me what line is causing the problem, pi equals 5. Read-only variable means, well, I've declared this as a constant and I can't overwrite it. So I wanted to show you an example then of a compiler error message that you'll see in case you ever accidentally try to overwrite a constant. It's something that programmers do from time to time, right? And so the compiler protects us from doing that. And const prefix protects us from overwriting variables we don't want to change, right? We wouldn't want to accidentally change pi and then have to use it somewhere in a calculation and come up with incorrect calculations. Right. So if we go back to the C programming language, right? And this is valid in C++ as well, we wouldn't be discussing it. Another way to create something that's a constant value is to use a pound define directive. So this is another preprocessor directive, right? We've seen pound include for including that IO stream header. So we've seen include directives when we want to bring in libraries. Pound define is another way to designate a constant value. It's not preferred by C++ programmers. So strict C++ coding says this is a bad thing to do. It's a bad thing to do because these are not always type checked, and there's a number of reasons that are a little bit advanced for where we're at right now. In our simple programs, it's really, if done carefully, it's not a bad thing to do, but then I'm more of a C programmer than a strict C++ programmer. You always have to do what your boss wants you to do, right? But let's take a look at them because you're going to see examples of them in people's code and you'll need to know what they are. Pound define, they can be placed anywhere in a program, but we follow a programming convention of placing them at the beginning of a program file. And so if we say pound define, we follow our identifier naming rule. So in this case, I'm creating an identifier named Max. I'm capitalizing it because we said the convention is for constants that we capitalize them. So pound define max 10, right? So anywhere we use the word max in code, what the preprocessor does is it substitutes the number 10 into our code, right? So that saves us from typing 10 in a lot of places. Pound define pi, 3.14159. So this is different than our const double pi equals 3.14159. And have you noticed that with a pound define directive, you do not use that assignment operator, that equal sign. If you do, the compiler will tell you there's an error. So we don't use the equal sign with pound define. The way that this works is once we define these, when we use these names in our code, whatever literals we have out here to the right are substituted in place of these words by the preprocessor. So you can create ints, doubles, right? Remember, this literal is an int, this literal type is a double, this literal type is a char. So wherever we use the word key in our code, it'll substitute in the character B. Pound define directive. Again, constant naming conventions, right? We usually write them in capital letters to distinguish them from other variable names. When you write a pound define, right, you cannot have a space between the pound and then the D in define. Right? After the define, you can have spaces, and you have to have a space when you go ahead and give this a name. Oh, and these are often called macros as well too. So if you're talking about a macro that's a constant, right, it's usually created with a pound define. Let's see. Now, blank space, that's what I just said. It's not a C statement, so it doesn't end with a semicolon. So none of our preprocessor directives. And so the pound or the hashtag, right, that says this is a preprocessor directive. None of those ever end with a semicolon, those directives. Why use constants? Here's just a simple example. We're going to assume we've written a program for a grocery store, and we've gone ahead and created some constants for the cost of sugar per pound and the cost of flour per pound. And I've just got the integer value 99 here. Now, that's not really clear as to whether that's 99 cents or $99. I hope it's 99 cents. But it all depends on how we use it within our program. We just said wherever we use this name, sugar cost per pound, 99. Wherever we use this name, flour cost per pound, the preprocessor will substitute in the 99. But suppose the price of sugar changes, right? And so if the price of sugar were to change, say from 99 to 52, we would go ahead and change this 99 to a 52. We would recompile our program, and everywhere in our program where we use the name sugar cost per pound, right, the preprocessor will just substitute in the new value. So yes, we do have to go to the trouble of recompiling our program when we make changes, but we want to think about, right, if we didn't use constants. First of all, these constant names are fairly easy to read. Sugar cost per pound, when you're reading that in a program, you know exactly what that name is describing. Like I said, if we just had to change the cost of sugar, if we'd written 99 everywhere in our program, if we typed in the literal 99 everywhere, well, when flour also had the same cost, is we started looking through our program trying to figure out which 99s related to sugar, if we just use the number 99, and which ones related to flour, it would be harder to update our program. It would be more error prone. So it's much easier to create constants either with a pound defined or with a const variable. And then if you ever have to change that constant, like I said, you would, if it's hard coded in your program like this, you change the value here, you recompile and create a new executable. Right. So we want to use constants whenever we can. They make our code easier to maintain and less error prone. Okay. Type compatibilities. Right? We try not to store the value of one type of variable in another type. Like we don't try to store doubles and ints and doubles. There are times when it has to be done, and we will learn about a typecasting technique that's appropriate at those times. But for now, we should not have to do that. We want to be careful when we do that. We want to be careful when we're writing our code that we don't do it, I should say. So here's an example of what we call a type mismatch. So we defined this variable named x. Its data type is int. And now we have a line of code that says assign the value of 2.99 to x. Well, 2.99 is type double. We said that x was an int. So what happens is the compiler will truncate everything to the right of the decimal point. It will just keep everything to the left, which is the integer portion. So what happens is x ends up with a value of 2. Well, if that's what we wanted to happen, that's okay. But if we forgot, because this is somewhere 30 lines later in our code, we forgot that x was an integer, and we end up assigning some double value to it, we think we should have a value of type double, we won't get the results that we expect. So we can turn on warning levels in our compiler. And typically what happens then when we turn on that warning level, the compiler will give us a warning. Now so here's the thing. If your compiler, so when you go to build your program, and when the compiler gives an error, your program doesn't finish building, meaning it doesn't create an executable program that can be run. But when it generates warnings, it goes ahead and builds the executable. So if there's warnings and no errors, it will build the executable. But you want to get rid of warnings. You don't want to have code that has warnings in it, because there are times then, because it's warned you, there are times that your program may not work as expected. It may work as expected 99% of the time, which maybe that sounds pretty good. except what if it's a program that's controlling the brakes on your car? Do you want to take the chance that that 1% time that it doesn't work, that your brakes go out because you didn't correct some sort of warning that popped up in your code? Right. So in this course, in your homework, there will be point deductions if you turn in code with warnings, because we will find there is no reason to do so. Right. All right, that's the end then of string literals, constants, and type mismatch. All right, so keep that in mind when you're writing your C++ examples. I will see you in the next lecture.